High tensions and high stakes, math becomes your best friend. Today, we're going to dive into the calculus of gambling profitability and show how math can better your payout. In many gambling games, we can model outcomes as continuous variables. So let's give the continuous variable x and the probability density function f of x, where f of x is modeled by an exponential distribution because the best models are given scenarios, because it represents continuous events such as bluffs, specific card plays, and play durations. It also assumes a constant rate independence of past occurrences. Now, to analyze our profitability, we need the expected value, and the expected value of a continuous variable is given as the integral from negative infinity to infinity of x times f of x dx, where f of x in this case, our distribution, which is lambda times e to the power of negative lambda times x, where x is greater than or equal to 0, and lambda is a parameter. Now, rewriting our integral and modifying our bounds based off our initial condition and rewriting the integral as a limit because it's an improper integral and substituting more information in, we get that the expected value is equal to lambda times the limit as t approaches infinity of the integral from 0 to t of x times e to the power of negative lambda times x dx. Now, to integrate this integral requires integration by parts. So we're going to say that u is equal to x, and dv is equal to what's left, which is e to the power of negative lambda times x dx. Now, integrating both sides with respect to the corresponding variables, we get that v is simply equal to negative e to the power of negative lambda times x, all divided by lambda. Now here, taking the derivative with respect to x on both sides, we end up getting du is equal to dx, which means we can now rewrite this as lambda times the limit as t approaches infinity of uv, which is negative x times e to the power of negative lambda times x, all divided by lambda, evaluated from 0 to t, plus 1 over lambda times the integral from 0 to t of e to the power of negative lambda times x dx. Integrating this further allows us to expand the integral again to lambda times limit of t as t approaches infinity of negative x times e to the power of negative lambda times x, all divided by lambda, evaluated from 0 to t, minus e to the power of a negative lambda times x, all divided by lambda squared, evaluated from 0 to t. Now, combining these two fractions together and distributing lambda back into the limit gives us a final limit of the limit as t approaches infinity of negative e to the power of negative lambda times x times the quantity of lambda times x plus 1, all divided by lambda, evaluated from 0 to t. Now, this final limit comes out to 1 over lambda. 1 over lambda represents the expected value of a gambling decision, in our case, the average time it takes for a decision to reach a profit or loss, which lies from the factor that lambda, in this case, will be a time-based parameter. We'll compare this with the expected value of a discrete variable in our scenarios to maximize our profitability. So let's say I have 2 games in front of me to play. I want to know which one will give me the most bang for my buck. Let's say that 2 games are poker or roulette. Let's look at poker first. In this game of poker, lambda represents the amount of profitable opportunities per hour at a rate where lambda is equal to 0.3, and the probability of winning a hand is equal to 0.35, and the probability of losing a hand is equal to 0.65. And our potential profit W is equal to $120, and our potential loss L is equal to $40. Now, the expected value in this case would be based off our discrete variable, simply equal to the probability of winning times our potential profits minus the probability of losing times our potential loss, which in this scenario, plug in information would leave us with $16. Now, the expected value of our continuous variable in this case is given by 1 lambda, based on here we derived it, where lambda is equal to 0.3, which in this case will equal to 3.3p. Now, interpreting this would mean that every 3.3 hours, expect to profit $16. Now, let's compare that to our game of roulette now. Let's compare this to a standard game of American roulette. In this case, lambda represents the amount of profitable opportunities per spin, since we're dealing with a wheel instead of cards now, at a rate where lambda is equal to 0.5. Now, the profitability of winning would be based on betting on a single number, which would be 1/38, and the probability of losing is simply 37/38. Now the payout is standard 35-1, the standard incoming bet of $1. Our potential profit W would be 34, and our potential loss L would be $1. Now, continuing that same math approach we did here, our expected value of our discrete variable would be about negative 0.079, and our continuous variable expected value would be 2. Interpreting this, we would get that every 2 spins, expect to lose about 7.9 cents. Now, based on this, this demonstrates that the game of poker would be significantly more profitable than a game of roulette, not only in the short term, but also in the long term as well. The significance of the expected value of our continuous variable in terms of lambda allows us to understand profitability of these two games in the long run, as it represents the expected value as an accumulation over time, and not just as a fixed value, but a long-standing trend in its own. This in turn allows us to be the best gambler we can be and maximize our profits on game day.